is always pretty high. So if anything seems funny from the Zoom end, please let me know. I was just, sorry to start over again. I was saying I'm happy to answer homework questions on the chapter 5 stuff. I will pass back the homework. I only gave it the most superficial flip through on the chapters 1 through 3 to give you credit on doing the problems, but I just ran out of time and I wanted you to have it back in your hands because of the exam tomorrow. You have my solutions that I emailed out to you, at least if you turned the homework in, which was almost all of you. And the chapter 5 solutions I want to give to you as well today. And that means that probably what I'm going to do is have you show me what you've done right at the end of class on chapter 5. And then I can give you my solutions after I get back to my office and have you turn in your work tomorrow at the exam. That way you'll just have your work to look at if you want to refer to that and compare with my solutions rather than just having my solutions before the exam. The other comment I was making is that not only do we have the usual office hours after class today, but I'm going to be using the late afternoon time, which is 2:30 to 4, to have optional office hours. So if you want to come for extra help, come right after 2:30. Dr. Katavid's class, I think, ends at 2:15, right? So that will give us enough time to come over to Young 110, which is 2 doors down from here. I will also start a Zoom session for those who can't come in person.
Would that be the same Zoom link?
Same Zoom link, yes. I'll be
Okay,
using
cool.
the same Zoom link the entire semester, so same one you use to come to class. And I'm just going to stay until everyone's gone. So I'll stay till at least 2:45. But as soon as no one's in the room and no one's left on Zoom, it's just inefficient for me to do my own work in that room. So as soon as everyone's gone, I will pack up and leave. So if you want to come to that session, come sooner rather than later. And that way I'll be sure that I don't miss you. And I'm happy to discuss lots of stuff on both homework and just generic exam questions. I should also mention that it was asked if there were any other questions that I really have in addition to the homework and the worksheets that would be appropriate for this class. And unfortunately, I don't. When I first developed this course material, I looked through a lot of textbooks on special relativity, and there are precious few problems that apply to the point we're at in the course right now. So I've made up as many as I had time to do, and I could probably make a huge review packet if I had the time to work on it, but I just haven't had a chance to do that. But so I would recommend that you rely heavily on understanding the homework very thoroughly, all those problems, as well as the worksheets we've done in class, which duplicate some of that, but just sometimes in a slightly different worded context. All right, anything else? Any other business we need to take care of? So tomorrow at the exam, I will email the folks who are Zooming, and I'm assuming everyone who's here today in the classroom plans to be here tomorrow in person for the exam, okay? So I will email instructions to the folks who have been Zooming in about what to expect for the exam in terms of how that will go. But be prepared to work on the exam during the time of our normal class so it doesn't interfere with Dr. Katavid's class. All right. Let's go back. And so we spent the end of yesterday's class period talking about or deriving, really, and according to the reading responses on this, you guys seem to find this section more confusing than the previous one on the time dilation. So, but I'm going to try to run the rest of the discussion of this in a way that's sort of analogous and parallel to the discussion we had on time dilation. You'll see there are a lot of parallels, and I think they'll help reinforce each other and hopefully liberate us from some of the confusions that come from just having what looks like a very simple formula for the length contraction. but can be misunderstood in a lot of ways. So the length contraction says, if you have a perfectly ordinary, nothing wrong with it meter stick or any other object, but a meter stick is good because it's easy to compare lengths with, it's marked out that way. And if it's moving along the direction of the length of the meter stick, and we compare the length as measured from the point of view of someone where it's moving to an identical meter stick that's sitting at rest with respect to the person who's doing the measuring, we'll find that the moving meter stick is shorter. And the factor by which it's shorter is 1 over gamma, where gamma is 1 over the, gamma itself is 1 over the square root of 1 minus v squared over c squared. So 1 over gamma is just that square root, but not in the denominator. That's a factor of 1 over gamma right there. And remember, gamma is always bigger than 1, so 1 over gamma is less than 1. And that means L prime here represents the length that the person measures for the moving meter stick, and L is the length of the corresponding identical meter stick that's at rest in front of the person. And we were at the point where I just wanted to pass out a worksheet. And this is the same worksheet, by the way, for those of you on Zoom that I emailed yesterday. So you have it. It has something about, it's called worksheet, I believe, 6.1, first length contraction problems. So try to pull that up while I'm passing it out. And then I'm going to put you into a Zoom breakout room. All right. Now I'm looking for it here, and unfortunately, let's hope it's in my pile of stuff here. Oh yeah, here we go. So there are actually 2 worksheets together. Worksheet 6.1 and 6.2 I printed out together. One's just on the back of the other. So make sure, for those of you in class, that you're working on 6.1 that I'll try to hand out to you on top. It's called First Length Contraction Questions. That means it's the easier cases rather than the more difficult cases that we'll see on worksheet 6.2 after a little more discussion. Okay, so the length contraction, one can sloppily summarize as moving things shrink along the direction of their movement. We also know from the previous chapter, chapter 4, that moving things do not shrink in the direction perpendicular to their motion, but they do shrink along the direction of their motion. And this tells us exactly how that happens. Okay, I'm going to send you guys to a breakout room. looking like at least a few of you are done. And that's good. You know, many of these questions are just, if you understand the answer, there's not much of a calculation to be done. A couple of them, there are some quick calculations, more of a calculation in the very last part, but certainly one we've done before.
Yeah, sure.
Okay, I'm gonna wait for the last person to be forced back into our group against their will. There we go. Okay, I'm just going to ask for shout outs, and you guys can certainly help me at home on Zoom. If you want to shout out, just unmute yourself and shout out an answer, and whatever people say here in the room. If we need more discussion, I'm going to do it here on the board. But we've done question 1A before, but I just trying to give you a little repetition there. We have seen that number 0.98c before, and so if you got the correct answer for gamma, which is what?
5.025.
5.025, yes, several people responded at once. We've seen that before, and so it should look familiar. If you're having trouble with that, that would be step 1 of something you want to disentangle yourself from before tomorrow's exam. But please stop me if you want to see more on that. I'm happy to elaborate on these. B says, if a person on Earth holds a 10-centimeter ruler along the direction the ship is moving, so the ship is zooming by Earth at 0.98c, and someone holds a 10-centimeter ruler oriented along the direction the ship is moving. So from the ship's point of view, that ruler is going to be moving along the direction of its length, right? As measured from the ship's IRF, what is the length of the ruler? Well, that's exactly what the length contraction is telling us. It tells us when we see this formula, L prime is equal to 1 over gamma times L. This is the length of the item along the direction it's moving as measured, you know, from the point of view of the frame in which it's moving. So this would be the ship's point of view in this case. So from the ship's point of view, what's the length of the Earth's ruler compared to an identical ruler also oriented along the same direction that's being held at rest in the ship? Well, of course, the one in the ship is going to be 10 centimeters long. This one we expect to be shorter, and it comes out shorter because gamma is bigger than 1, so 1 over gamma is something less than 1. 1 over 5.025 times 10 centimeters. Okay, and that number is very close to 2 centimeters. 1.99 centimeters is what I have here. Any questions on that? That's just making sure you understand in the most straightforward way what this formula is saying. I mean, that's not completely trivial. There are ways to misunderstand what that formula says as well. C, a person on Earth holds a 10-centimeter ruler perpendicular to the direction the ship is moving. As measured from the ship's IRF, what's the length of this ruler? 10 centimeters, several people shouted out, yes. 10 centimeters, that's the result of chapter 4 that says that objects don't shrink along the direction perpendicular to the direction that they're seen as moving by somebody else. There's no fundamental movement, but you can take the perspective of someone in an inertial reference frame where something's moving. And this is saying that dimension along the perpendicular direction doesn't change. D, a person on a ship holds a 10-centimeter ruler along the direction Earth is moving. Of course, the person on the ship thinks they're at rest, or they feel that way, but they do see Earth zooming by, and they orient their ruler along the direction Earth is moving relative to them. As measured from Earth's IRF, what is the length of the ruler that's being held up on the ship? Jack? Yeah, that's exactly symmetric with the question that was asked in B. The only thing that switched is whether someone on the ship was doing it and was being observed from Earth versus someone on Earth doing it and it was being observed from the ship. So in that case, the answer is exactly the same as B, which was 1.99 centimeters. All right, E, a person holds up a 10-centimeter ruler along the direction the ship is moving. They're holding it up on Earth. Suppose the ship is traveling by Earth at a different speed, not 0.98 c anymore, so gamma is no longer 5.025. What should V be so that the ship observers measure the length of the ruler to be exactly 5 centimeters long? Express your answer as a multiple of c. So how would I start this problem? What do I know I want to be true? If I want the length of the moving length in the frame where it's moving to be exactly half of the length in which it's seen at rest, what do we want gamma to be? 2, right. So we want gamma to be equal to 2. So all we have to do is solve this equation. Gamma, we want to be 2. That will make 1 over gamma 1/2, which means the frame in which it's moving, it will be measured to be exactly half of the rest length. We want gamma to be equal to 1/2. Well, gamma, let's expand that out in terms of v. Gamma is 1 over the square root of 1 minus v squared over c squared. Or maybe I could just write it as v over c squared. And our goal is to solve for v over c, because then if I put that number for v over c in front of a c, that will be v, but it will be expressed in terms of c. Okay, so to solve this equation, of course, you could cross multiply, and we're trying to solve this equation here for what v over c is. But even easier, if two things are equal, their reciprocals are equal, right? As long as you do the same thing to both sides of an equation, it doesn't matter as long as you're doing exactly the same things. If they started out equal, they're going to end up equal in the next step, as long as you do the exact same thing. So let's take the reciprocal of this side and the reciprocal of this side. That means that 2 has to equal that square root. Okay, what would the next step be to solve for v over c? Square both sides, right? So that means I'm going to go up here. Squaring 2, I get 4, and squaring the square root just undoes the square root, right? And I get 1 minus v over c squared. And then, well, I'm going to try to put this on a side by itself. And maybe the easiest thing is to add it to both sides so it appears over here, and then subtract the 4 off over there. There's several ways you could do it. But if I bring the v over c squared over to this side, it comes over with a plus sign because I've added it to both sides. And then at the same step, I'm also going to subtract off 4 from both sides. So v over c squared looks like it. Ooh, that doesn't look good, does it? Somewhere I've gone wrong here. What did I do wrong here? Oh, yeah. The gamma, we want gamma to be 2. Thank you very much. And that means this is 1/2. Thank you. We want gamma to be 2, and that makes 1 over gamma 1/2. Thank you. Sometimes when you're at the board, it's really hard to see things from this perspective. Okay, so that means that When we square both sides, I'm going to get a 1/4 on this side, right? And then when I subtract over here, I'm not subtracting off 4, I'm subtracting off 1/4, which is perfectly fine because I'm about to take the square root, and I don't want to take the square root of something negative. 4/4 minus 1/4 is 3/4, so this side is the same as 3/4, and that means that V over C is equal to root 3/4. As a decimal number, that's 0.866. And therefore, V is the same thing as V over C, which we just found, multiplied by C. Isn't that true? If I want to find V, I can do it that way. Well, I'm just going to leave the number we have there for V over C. That's 0.866 times C. So that's our answer. Just sort of practicing with that not too hellacious algebra, but still, maybe kind of rusty for some of you. Questions on anything on that worksheet? That's step 1. That's the kind of easier things, but there are some paradoxes or apparent paradoxes that we are going to get into now, and they're the same kind of thing that we did in the last chapter. So I'm going to try to parallel the discussion with what we did in last chapter. Let me go back to the slides now and continue on. This was not a reading response, and I'm going to hit your reading responses a little bit heavier at the beginning of Monday's class after the exam is over, but I thought this was something someone asked the last time I taught the class, and it's a great question. It's a natural question, so it may be in there with your reading response questions that I'll hit. I just sort of superficially look through them. Why are we limited to using meter sticks that are perpendicular and parallel to their motion? What would happen if we use meter sticks at other angles relative to the motion? Perfectly natural question. Seems like we've left something out. Or more generally, forget about a meter stick. Maybe we have an odd-shaped object like this astronaut, and the astronaut's doing the moving along a certain direction from my point of view. And I want to know how, if I make careful measurements of the astronaut using people in my inertial reference frame, how is the astronaut going to be measured? What's the geometry going to turn out to be? Well, the idea is, I'm initially going to do a case where the astronaut is moving along the horizontal direction. So what I can do is plaster over the top of the astronaut with a bunch of meter sticks and have those meter sticks moving along with the astronaut. And I know that the meter sticks that are perpendicular to the direction he or she is moving, and I'm going to make that the horizontal direction, so those vertically oriented ones are not going to change their length, but the horizontally oriented ones are going to change their length. So for example, if this astronaut is moving to the right at a speed corresponding to gamma equals 2, we expect a contraction by a factor of 1/2, 1 over gamma in the horizontal direction. So that all that means is that the entire picture is compressed in the horizontal direction without changing the vertical dimensions at all. If you measure vertical distances between any points on the two figures, they should be exactly the same if you've done the transformation the same. What if the astronaut's moving in a different direction? For example, up and to the right, and maybe at a more extreme gamma, higher speed corresponding to gamma equals 4. So here's the same astronaut. Now I'm viewing that astronaut from the point of view where that astronaut is traversing relative to me up and to the right with a gamma corresponding to 4. We could figure out what V that corresponds to. And along that direction, the astronaut is compressed by a factor of 1/4, but not compressed at all along the perpendicular direction. I'm trying to show that by the dashed lines there. And one way to, if you have a figure like this, of course I did this by compressing things in a Word document and squeezing one dimension and not the other. But if you're doing it by hand, and there is a question in the homework for chapter 6, which you'll see when you get into this maybe over the weekend after our exam is over and start looking at those chapter 6 problems. You can draw a little perpendicular reference line like I've done down here. One that's perpendicular to the motion. And I know if gamma is equal to 4, everything should compress by a factor of 1/4 along this direction, right? And so what I can do is say, well, if I want to, I could draw the corresponding reference line up here, and maybe I should have done that. But what I could do is say, well, where's this point on the top of the helmet going to be in my new drawing? If I drew the same reference line that just barely touched the foot down there, perpendicular to the motion. I could say, measure, on my paper, measure this distance with a ruler. Say it's 8 centimeters from that blue dashed line to the tip of the helmet. Then in this drawing up there, it should be exactly 1/4 that distance. Uh-oh. Something's going wrong with my pointer again. But in any case, that distance from the farthest point on the helmet to my reference line would be 1/4 whatever I measured. And I could do that for a bunch of different points until I get a nice picture of, oh, okay, I can see how the helmet, which was roughly a circle here, is now deformed into an ellipse. If you do enough points, I won't make it. You'll see in the homework when you open it up, instead of a detailed drawing of an astronaut, you've got a stick figure with just, sticks for arms and legs. So it's not as hard. If you do a few points and figure out where the ends of the sticks are and kind of where the head is, you can figure out how to draw the drawing for various kinds of motion. So once we've done the perpendicular and parallel cases, which we have in chapters 4 and 6, we're really done. And that covers something's going on with my there we go. No, something's going wrong with my presentation. I'm going to end the show and start the show again. I'm not sure what's going on there. Very strange. Too much technology, I guess. Let me take that out. Why can I not advance my slideshow? All of a sudden, it's not happy. Sorry for the technical difficulties. And now it's like I'm zooming in. Some setting has been changed here, and I don't know what it is. Very strange. And it's been messed up by my, it's like I'm holding down the control button. Is it caps lock? Oh, maybe caps lock is on. No? It's like I'm holding down the control button. That is really strange. Because I don't know what's going on, I'm just going to sort of continue, but instead of using slideshow mode, I'm just going to have to click through my slides in here. So I apologize for that it's not as slick as maybe normal, but the idea here is going back to the original question that was asked here. What about a meter stick that's neither vertical nor horizontal, that's oriented in a direction that is at some weird angle to the direction of motion, which I'm taking to be to the right here? And the answer is that in that particular case, it shrinks along the direction of motion. If we think of it as surrounded by a rectangular box, we compress the box along the direction of motion, but leave the dimension perpendicular to the motion exactly the same. Any questions about that? So even though parallel and perpendicular seem to be two very specific cases, they really cover all the other cases you can imagine. And so we now know in general how a three-dimensional object is going to be measured to be deformed in a frame, viewed from a frame in which it's moving. Okay, let's address the same paradox that we addressed with the time dilation problem, and that is that it seems like if we say A observes B's meter stick to be shorter, then by the principle of relativity, B has to observe A's meter stick to be shorter because they're performing essentially the same experiment if they hold up their meter sticks in the same way. Isn't there some contradiction there? And the answer I'm going to give is exactly the same as what we said before, but phrased in terms of lengths of sticks. It sounds like there's a logical contradiction if we say B's stick is shorter than A's stick is shorter than B's. But when we make those statements, we're saying it in such a way as if the length of an object is an inherent feature of it, rather than being a feature that changes as you move from one frame to another. You know, just like the velocity or the speed of an object isn't something that's inherent to that object at the time that it's moving, but rather its velocity or speed is going to change as you view it from different points of view in which you're moving. It's the same, we're saying now, with the lengths of sticks. And so we should probably say instead, there's no logical contradiction when we rephrase it as B stick is shorter as observed by A, and similarly for A as observed by B. Unless you're assuming that judgments about space and length are shared by all, and we're asserting that that's not true here. In order to satisfy the principle of the constancy of the speed of light and the principle of relativity, we're going to have to assume that that's not true. And we'll again address the fact that there's experimental evidence to back this up. Okay? Now, certainly, we do need to be careful with language. There's no one length of a meter stick. You have to specify the inertial reference frame that it's being measured from in order to say what that statement means. But I'm sympathetic to the fact that the length of a thing when it's not moving is an important special case that we're used to dealing with all the time, right? That's the normal way you measure a length. Just like the length of a tick on a clock that's not moving with respect to you is an important special case. And in fact, those cases are so special, even though they're not general, they do come up enough that they're given their own names. And so we're going to start to introduce some terminology that has the word proper in it, and special relativity that has a special meaning.
Professor Kelly, can I ask you a quick question?
Absolutely.
You're no longer sharing your screen. Is that intentional or not?
Well, that's really weird because it says that I'm sharing my screen. Let me.
So I don't know if it's just me.
I could see it.
Oh, you can't. So it's just me. Okay, never mind. Ignore me. I'm being clumsy.
Let me try. I unshared it, and now I'm going to share it again. And that hasn't solved my problem. Can you see it now, Eva?
I can see it now. Thank you.
Okay. Yeah, I don't know what happened there. Things are behaving very strangely. Fortunately, I can at least hobble through, it looks like. Somehow my new presentation remote is messing things up a little bit. But I can get through. Okay, so let me find out where. Here we were, yes. The proper length of an object is going to mean the length of an object as seen in an inertial reference frame or measured in an inertial reference frame in which it's at rest. That's the normal way we measure lengths of things, right? But now we're considering the differences when we measure it from other points of view. Similarly, the proper time interval between two events is the time interval as measured in an inertial reference frame in which these events occur at the same place. So this would be like Alice is traveling from Earth to Procyon. The time interval as assessed by Alice, who's doing the moving, who is present at both of those events. Alice leaves Earth, Alice arrives at Procyon. How much time elapses between those? We know Alice's assessment of that's going to differ from the Earth's assessment. The proper time interval here means the time interval measured by the one special frame that happens to be present at both events. In other words, left just as the one event was happening and arrived just in time to be at the second event, okay? And similarly, when we say the proper frame of a uniformly moving object, just simply means the inertial reference frame in which it's at rest, so that we can say, oh, we got a ship that's moving. Let's consider the proper frame of the ship. That means you're moving along with the ship and taking that point of view. An interesting special case or thing to note about these proper lengths and time intervals is that among all the length measurements of an object made in different inertial reference frames, the proper length is always the greatest. Put another way is If you're at rest with respect to the object, it has its normal length. Whereas if you view it from any other point of view, it's moving, and you're going to see it as shrunken along the direction of motion. So it's going to have its biggest size when you view it from the point of view in which it's at rest. There are lots of ways to move and view it where it's not moving, where it is moving, but there's only one way to view it where it's at rest. Similarly, for the proper time interval, among all the time, if you have two events, like Alice leaves Earth, Alice arrives at Procyon, there are lots of different inertial reference frames I could view that set of events from, and each of them could measure their own time interval that they have between the two events. The proper time interval is always going to be the smallest of those time intervals that are measured. We've seen one special case of this. We said, you know, if Alice is going from Earth to Procyon, she's going to assess less time as having elapsed between leaving Earth and arriving at Procyon compared to the Earthlings, who will assess a longer time period as having elapsed. That's weird, but it's true. The claim here is that, well, you know, that other inertial reference frame could be something else besides the Earth, and it's still going to be greater than compared to the one in which they occur at the same location. Okay, so we'll add to this list a little bit with that proper terminology. Okay. All right, let's go back to the idea of the paradox. There seems like there's an analogous paradox to the one that we saw with the time dilation. Well, what about distances between events? Here again, I guess in this case, Bob is moving between Earth and Procyon, and Alice, say, you know, we're imagining Procyon, or this distant star, has an Earth sign. They're in the same reference frame, so these are both in frame of reference A, and they have separate scientists near those locations, as well as everywhere in between. And we define event 1 as Bob leaves Earth, event 2, Bob arrives at the distant star. And let's imagine this conversation, and we're going to start the conversation this time with Bob making a claim. I measure the distance as 4 light years as I travel. Okay, you know, you could extend a bunch of meter sticks out and in principle measure that distance, and you could do it by clever measurements with light beams and things like that, but there are lots of ways you could measure that distance. You could also do it with distance equals speed times time, and then measure the time it takes you to get there and infer the distance. So I measure that distance as 4 light years. You're moving A with respect to me, right? Earth and that distant star are moving. They're like an object that's moving past. The meter sticks that are attached to those objects are also moving with respect to me. So A's meter sticks are going to be shortened. And when you measure something with a shortened meter stick, sounds opposite, but if you think about it again, you'll see it's the right way. If you measure something with a meter stick that's too short, you're going to think it's longer than it actually is, right? In the same way that it's somewhat confusing, if you measure a time interval with a clock that's running slowly compared to someone else, the tick lengths are going to be longer, but that means the time intervals you measure will be shorter. Okay, so you have to know which way you're trying to use that. Am I interested in the tick lengths or time intervals between events? So here we're talking about whether the meter sticks are shrunken when viewed from a point of view where they're moving. So B is saying A's meter sticks are shrunken. Therefore, A is going to assess the distance between Earth and the star as being longer because more of those meter sticks will fit between, right? It's a simple idea, but it's really hard to digest in your mind because we're not used to thinking this way or thinking about shrunken meter sticks at all. But this is our new reality. So B says, I think A is going to assess the distance as 8 light years because they're using meter sticks that are too small. More of them will fit between the Earth and the star. Okay. Then A says, yes. Somehow I went too far here. Yes, from Earth, we measure 8 light years. But wait a minute, I'm looking at your meter sticks as you fly by, B, in your spaceship. Your meter sticks are shorter too, by a factor of 2. And so you're going to measure 16 light years. And that can't be true because B already said, I measure 4 light years. I can't simultaneously measure 16 light years. So there's some asymmetry in this particular case. Only one of them is right. And the question is, just like before, why, in this case, A is misapplying the length contraction here. The length contraction is true, but the conclusion that's being drawn from just using the length contraction is not true. Okay, why isn't this the situation symmetric? And again, the answer is going to come down to that asynchrony between the clocks. Everyone wants to synchronize the clocks in their own frame, but if they're synchronized in that frame for their convenience, they're going to be asynchronous in another frame. And we'll see why that's happening in just a second. Okay. Now, to think of this distance just as an object, well, you know, we're essentially assuming that Earth and this distant star are in the same reference frame. So they're at rest with respect to each other. And so I could consider the object consisting of Earth plus the distant star to be a single object. I mean, there may as well be a rigid rod connecting them because they're not moving with respect to each other, right? So they're moving along the same way a car is moving, right? It's just we're only keeping track of the two ends of this particular car or spaceship. So the first point of view I'm showing here at the top is the point of view of observer A or IRF A, in which Earth and that star are at rest. They assess the distance to be some distance L, and the spaceship that's moving between them, is, you know, in this case I'm imagining it's moving with a gamma factor of 2. They might see a different length. Let's go to B's point of view. When we draw the same picture from B's point of view, B feels totally at rest, but sees A's objects, the Earth and the star, rushing by. And they may as well be connected by rigid rods because their distance isn't changing. The length contraction is saying that that distance now should be shrunken along the direction of motion compared to, notice I've drawn Earth and the star from this person's point of view as ellipses, because they're not going to see them as having a circular cross-section anymore, but they'll be shrunken by a factor of 1/2 along the direction of motion. But so with that distance, and so that distance L prime is going to be shorter. So if we think of this as the object that's doing the moving, then from the point of view where that object is moving, we're expecting a shorter length to be measured from that perspective in which it's seen as moving. So that's the B perspective here, okay? Keep forgetting how to advance these, okay? And the length contraction formula is designed to be applied in the case where the object is moving. And what I mean by that is that this is the length, the L prime, the thing that's solved for here is the length measured from the point of view which the object is moving. It's the length that is measured when the object is moving with respect to the person compared to the length when it's at rest with respect to the person. Okay, and therefore the length contraction formula can be used to determine the distance, when I think about it this way, between two co-moving objects. As long as I think if those objects are moving together kind of as a rigid unit, I could just think of them as a whole object, a solid object, and it's going to appear shrunken when it's moving. Okay, so that's saying it certainly makes sense to say that from B's point of view, these two things should be shrunken. From A's point of view, that object that we're talking about is not moving at all, so that should be the longer of the two. So that seems to break the symmetry. Now, I'm sympathetic if you're not completely satisfied with that. So here's an objection that I'm raising. From A's point of view, that means Earth's point of view, B's meter sticks are short. A looks up at B's meter sticks oriented along the direction that B is moving and sees those sticks as being shorter. And so more of them are going to fit between the Earth and the star, right? And therefore, shouldn't B measure the longer distance? We just said that B is going to measure the shorter distance. But from this point of view, it sounds like B is going to measure a longer distance. There's something wrong with this argument. And what's wrong with it is, again, the fact that in these events, there's going to be two clocks in the A frame that are present at the events we're describing, but only one in the B frame. And we'll see how that plays out in just a second. Okay. So it certainly is true that A, or the Earth frame, sees the spaceship's meter sticks as shortened by a factor of 2 along the direction they're moving. When the length contraction correctly predicts, But this doesn't mean that the distance seen by A, so we're taking B's point of view here. What I'm doing is saying, from A's point of view, B's meter sticks are shrunken. So here's B zooming by. I've put a bunch of meter sticks underneath B here, and I'm imagining they're moving along with B. So those are B's meter sticks. They're moving along, staying up, keeping up with B. And I've even put a couple of clocks on here. This is a B clock attached to B's meter stick over here. It happens to be passing the Earth at this time. Here's a B clock attached to B's meter stick, which is moving in this point of view, and it's attached at a point, happens to be passing the star at this time. That doesn't mean that the distance as seen by A on B's moving meter stick is the distance that B is going to measure for that distance, so that B would see it as longer, right? From this point of view, it looks like, hey, these meter sticks are shrunken. B is going to assess this distance as being longer than the Earth measures it, because B is using short meter sticks. Why not? Well, it comes down to this picture that I showed you earlier of, well, normally we don't have to say this because we measure the length of objects always when they're at rest with respect to us. But if something's moving, we have to be very careful to measure the front end and the back end at the same time. And if clocks are asynchronous from the point of view of the frame in which they're moving, we really have to think carefully about this, okay? So in this case, B's clocks are asynchronous from the point of view of A. So again, I'm drawing the picture up here on the top from the point of view where A, the star and Earth are at rest, and B is zooming by. All those meter sticks are B's, and the clocks attached to the meter sticks are B's. They're asynchronous. The one that's trailing behind on that motion, as seen by A's point of view, is going to be ahead by a certain amount of time, okay? So this one reads a later time. This one up here, as it's moving by, reads an earlier time. This is crucial because if B is going to measure the length of things, B is not going to say, hey, I'm going to measure this position here and this position here, because those would be at different times according to B. Those are B's clocks. B has to measure them at the same time. Now, notice this is at a later time. So imagine that B decides to measure the location of Earth at this particular time, quarter past, if we think of it as kind of pointing that way, quarter past the hour. Then B is going to measure the position of this star at quarter past an hour. Now, it's 15 minutes earlier than that, so B is going to have to wait a while. And meanwhile, this meter stick's going to move up, and they'll measure the position to actually be much shorter than you might naively think by using the length contraction. So it's absolutely true that the meter sticks are shrunken, but you have to think of that in the context of also the asynchronousness of the clocks, that as seen from the frame where they're moving, assuming that you have them synchronized when they're at rest. And any normal person would want all the clocks in your own reference frame to be synchronized. Otherwise, it's just, you get crazy complications. So, oops, I keep shrinking that down, but I forget I have to click here. Okay, so if we take them both into account, we're going to understand that actually, even though it looks like B would measure a longer distance just from the length contraction formula, B is actually going to measure a shorter distance if you make sure you make the ends measurements at the same time as assessed by B. Okay. Now, again, just to finalize this objection, now it's also true that A's clocks are asynchronous as seen by B. So I'm drawing the picture down here at the bottom where B is at rest. A is moving by. Both the star and Earth are moving by at gamma equals 2 to the left from their point of view. The meter stick on the bottom is no longer belonging to B. Now it belongs to A. So this is a big, long meter stick that A is carrying along with it, and the clocks on the meter stick belong to A as well. So the meter stick, the clocks, and the Earth and star are all moving together. Gamma equals 2 to the left. And B is going to say, hey, your meter sticks are shrunken. That's absolutely true. From that perspective, they're shorter when we make the most precise measurements that anybody can. They're going to be measured to be shorter. The difference is that the meter stick and Earth and the star are all moving at as a unit. So that means that even though from B's perspective, it's a different time on Earth's clock at Earth than it is at that same time as assessed by B on the star, So these, as B sees it, the Earth the star measurement would be taken first, and the Earth measurement taken later for the position in measuring that length. It doesn't matter because they're all moving together. So if I have a fish that's moving and I move the meter stick along with it, it doesn't matter if I measure the front of it and then later I measure the rear, as long as it's moving along with it. And in this case, those shrunken meter sticks are moving along with it, so we don't have to worry about the asynchronization from this point of view. So this is telling us we can naively apply that length contraction formula in one special case, okay? When two events are defined by an object in one inertial reference frame, again, traveling between the two objects at rest in another inertial reference frame, like a spaceship going from one location to another, we can use it to compare the distance between the events as seen in 2IRS without correcting for the clock asynchronization, but only in one special case, just like with the time dilation application. Only in the case where the length being measured is the distance between those two objects that it's traveling between, and it's viewed as moving by the object that travels between them. In other words, in this case, I should take the point of view of B and think of the two objects it's traveling between as some rigid body that's moving. And then the correct way to interpret this formula, L prime equals 1 over gamma times L, is L prime is going to be the distance between those two objects as measured by the thing that's moving between them. And L is going to be the corresponding distance between the objects measured from the point of view where the Earth and the star are at rest. Okay, that's a lot of words, I know, and it's going to take a while to sort of digest that. But see if you can write that down in a way where you're doing problems, you hang on to that. And part of that that's going to help us practice with that is the worksheet. So in this case, that was phrased in terms of a length of an object, right? And the object here isn't really a rigid object, but it may as well be rigid. We could also rephrase that in terms of the distance between two events. Here's a first event where the spaceship leaves Earth. Here's the second event where the spaceship arrives at Earth. Those are two events that can be viewed from any different reference frame. And we might ask about the measured distance between those two events. And the correct relationship is that the point of view where the locations of those two events aren't moving is going to be the greater distance, whereas when you view them from the point of view in which they are moving, that's the B point of view, the distance between those two events is going to be less. Remember, gamma is bigger than 1, so 1 over gamma is less than 1, and that means as viewed from this B point of view, we're going to get a smaller distance as compared to the length measured from the A point of view where those two, leaving and arriving destinations are at rest. And B is moving between them. Okay, I think we're up to a worksheet. And you already have the worksheet. I think this is a separate worksheet if you're looking in the email stuff that I emailed to you, but those of you in the class, you're just going to flip it over now. This concerns distances and time intervals between events. So you're going to have to cling to this fact that's being displayed up here. Which means if I'm going to apply the length contraction formula to conclude something about how far it is from one planet to another or something like that, I can only apply it in one particular way, even though superficially it seems like you might be able to do it in 2 different ways. All right, I'm going to restart the breakout rooms and come check on you in a few minutes. I should say that A and B are calculations you've done before on a previous worksheet, but just getting you used to that unit, which was, you'll see a lot in relativity, light years as a distance unit. Don't let that throw you off. Remember, 1 light year is the same thing as c times 1 year. That's just distance equals speed times, and that sometimes simplifies your life when you write it that way. We don't need to write out the answer to B again. We just did it. It's 5.025, just like it was on the previous worksheet. Get everyone back. That's all rooms. And then 3-pin my video. Okay, looks like everyone's back. So that was the answer to C. Any more questions on C? So when you do this calculation, you get 2.27 light years. I'll just put that as LY. D, use your results from C and distance equals speed times time, which is always true as long as you use all 3 quantities as measured from the same IRF. Use distance equals speed times time to determine how much time it takes the ship to get to Procyon as measured from the spaceship point of view. Well, we've got the distance they've got to move. We also have the speed they're moving at, which is 0.98 c. So we can figure out the time from distance equals speed times time. We just got to use all of 3 of them from the spaceship's point of view. So I'm going to write down in D, distance equals speed times time, and let's fill in the blanks. The distance they have to move, we're talking about the spaceship, and this is their point of view. So that's 2.27 light years. Now I'm going to write light years. What does a light year mean? A light year means the distance light travels in a year, and so I can write that using this distance equals the speed that light's traveling at, which is c, times 1 year. Sorry, 1 year is what I meant to write down there. C times 1 year is 1 light year, right? This is the speed that light is traveling at times the time that elapses, give us the distance it goes, and by definition, that's 1 light year. Okay, that's our distance, and now let's set that equal to the speed that they're moving at. That's 0.98 c. I keep using the same numbers. That's somewhat convenient, so we don't have to recalculate stuff. Times the time that elapses. I might call that T ship. And when I use that, well, the nice thing about writing it this way is that now I've got a factor of c on both sides. I don't have to put that in there. It cancels out in this particular calculation. In this case, the time for the trip as assessed by the ship is going to be 2.32 years. When you put the numbers in and solve for T ship, you got to divide by 0.98 on both sides. Okay, so compare that to the answer for part A. That's going to be a factor of about 5 bigger, 11.63 years. And the question is, well, in E, you're asked, well, does that comparison between D and A square with what we already know about the time dilation formula? Right, we're saying, as assessed by the people on the ship, it took a shorter time. As assessed by people on Earth, it took a longer time. Yes, that assesses with what we know by the time dilation formula. There's a little bit of a confusion sometimes people have. The original time dilation formula looked like this: T prime equals gamma times T. But this doesn't mean the time interval that's measured to be elapsed. This means the time it takes for one tick on the clock. Okay, so since, from the point of view where a clock is moving, compared to, if it's 1 second per tick, if gamma is 5, it's going to take 5 seconds for one tick to go off when you're watching it from the point of view of someone who's where the clock appears to be moving. So that means if we're watching the spaceship's clock, it's going we're going to have to wait 5 seconds to see a 1 second tick on the spaceship's clock. And that means if we think about what that means about the time intervals the spaceship will assess, if their clock is ticking slowly, they're not going to see as much time tick off between those two events. And so one way I wrote this in the slides that we were using over the last couple of days is the time interval between the two events, leaving one place and arriving at the other, has the opposite sort of relationship as the tick length. As the tick length gets longer, the time assessed by that person gets shorter. So this means time as measured by the spaceship from the spaceship point of view is going to be shorter than the time as measured by the person who's not doing the moving. And that does agree with what we had before. If you compare, this is the answer to part A, this is going to be the answer to part D, and they do agree that one is just a factor of 1/5 shorter than the other one. Okay, so that's E. And I haven't read F yet. Spaceship passes an asteroid which is at rest in the Earth IRF. The crew members measure its length along the direction the ship will be traveling while moving and finds 0.78 kilometers. So that's going to be a length contracted length, right? That's not the proper length of this asteroid. That is a length contracted length. How long is the asteroid as seen from the Earth's IRF along the direction it's moving? What's that dimension? And the answer is, it should be longer. And one way to sort of get these questions right, all these relationships we've done so far, you're either multiplying by gamma or you're dividing by gamma. So if you can correctly decide ahead of time, I know it's going to be longer. Well, what do I do to make something longer? I multiply it by gamma. So you better be doing that, right? If the measurement from the point of the ship is 0.78 kilometers, I know I need to multiply that times gamma, which in this case is close to 5, to get the length as measured by Earth. Okay, the normal way we would write this formula is, if we were writing it as a length contraction kind of thing, is here's the length from the point of view where it's not moving, right? The asteroid's not moving in the Earth. You multiply that by 1 over gamma, and that gives you L prime, the length from the point of view in which it's moving. So that means Earth is going to be 5 times as long. Instead of 0.78, you get 3.92 kilometers approximately. All right. I think I have one more comment in here, but we're 5 minutes after, so I'm going to call the class now. Doesn't matter. We have an exam tomorrow, so we're not worried about chapter 6 so much, and maybe we're worried about chapter 5. So once again, I want you to ask your questions on chapter 5. That's important, and anything you have on chapters 1 through 3. And I'm going to hand back the homework now before I forget to those who are in the room. Those who emailed it to me, you still have a copy of your homework, so it's not so crucial that I hand it back. But please hang out, ask any questions pertinent to the exam or pertinent to the homework, which is certainly pertinent to the exam. And just bear with me while I hand a few things out, and then we'll rejoin for office hours. If you're taking off, feel free to do that. Emily? So bring that chapter 5 homework with you to the exam tomorrow, and I'll collect it legitimately then. And I think, is this part of yours that just got disconnected? Yeah, okay. Colby? Everett? And I am going to send out the chapter 5 solutions today, just so you've got my version of it to look at if you want to compare with your work. Joseph, Spencer, you're welcome. Jacob. And I think that's, oh, Jack, you, did I hand yours back? I didn't hand yours back, right? I have yours somewhere, but it's not in this pile. You gave it to me. It must have been disconnected with the other one. Here it is. You can, I'm going to give it back to you, even though it doesn't have a score on it. You are going to get a 10 out of 10 because you've attempted all the problems. Check with me again to make sure I put that in the grade book, because it's always possible that I say that now and then I forget. So call me out on it later on. Okay, let's see nobody's on Zoom. Maybe they're going to come later. Say that again. Probably not. I'm just going to trust that you've done it, and I'm going to send it out and I'll collect it tomorrow. It truly will not be to your advantage to look at the solutions I put out and copy it, because you'll get peanut points on the homework and then the exam is worth quite a bit, and you should expect some of that stuff to appear on the exam. 110, yeah, so 2 doors down, 230. See ya. Bye-bye. All right, good. Let me get my copy of the problems out.